Right. So, yes. Hi, everyone. Let me try to share this. Okay, so Steffi, can you confirm you're seeing the screen?
Yeah, I'm seeing the screen.
Okay. So what I want to talk about today is something called matrix augmentation. So it sounds complicated and fancy, but it's actually a very simple concept, which can be very useful for the analysis of imaging or 3D data set. So we just show basically how it works, the concepts behind it, with some examples, and we try to do some practical demonstration using Sims and VA. But the idea here is just, obviously, we show some examples of my work, but I want to perhaps inspire you to do exactly the same with your work, because it's been very useful to me doing this. So in MVA, typically, as we spoke last time, I gave a seminar here in the MVA general overview. Use observations when you're talking about spectra. We do a spectra of different samples, and then we do PCA and MF, things like this. When we're doing mapping data sets or imaging data sets, we treat the pixels as observations, and most times we just use it from a single sample. So we'll map a single sample and then do PCA and MF, etc. in this specific data set, which is related to one individual sample. So what we want to do with the augmentation is explore how to combine these approaches, so we can do imaging of several samples, but treat them as a single data set. So just as a recap, maybe if you're interested, we can put in the workshop teams the links for the talk I gave about all the background in MVA. But this is just a quick recap on how we construct a data matrix before we do MVA. So basically, you have a sample, you have all the spectrum, and you select a specific number of peaks, and you store all these peaks for one sample, and then you do it for the next sample using the exact same variables, as we say, which are the peaks. So let's say we do it for 6 samples or more. We end up with this matrix where the rows are the samples and the columns are the peaks, so typically the peak area. So we export something like this to be our data matrix. So again, each row will be related to a sample, so it's just another way of seeing the spectrum in this matrix form, all the spectra from the samples in this matrix form. So once we have this, so again, in the other workshop I explained why we do this, because then we factorize to find the principal components. So once we have this, we can then do the augmentation. There are 2 ways of doing this. One of them is the column-wise. So basically we are increasing or adding stuff in the columns, which in this case here are the variables, right? So we can add more variables. So it could be as simple as just adding more peaks to your data set, so you do it for all your samples. But it can be other things. It can be, you can add another spectrum that was simultaneously acquired. It's not the case with tof-sims, where we can only detect things from one detector, but some instruments will detect both positive and negative polarities at the same time. So you can just get data from these 2 detectors and construct a longer spectrum that will be used for MVA. So you do this augmentation column-wise, or you can combine different techniques. You can have all your Sims data and then attach it to Raman data if you have it for all the samples, or EDX or other things like this. Or you can even go beyond and do things which are non-chemical, analytical. It's not analytical chemistry variables, such as, I don't know, some biological response, or even socioeconomical variables, or treatment time. If you have some profile for treatment, it can be a single number, but typically if you have a spectrum or a series of variables related to each of these samples, you can add it to here, as long as you do it for all the samples. And then each case you have its own challenge, and mostly when you combine things like this, you have to be careful about appropriate normalization, because let's say in your sims, if you combine sims and Raman, for example, in sims, let's say the maximum or the average peak intensity, let's say it's 10,000, and in Raman is 100. This is a huge difference. So you have to think of ways to normalize the data set before you do the matrix augmentation. Otherwise, the Raman data will be too weak in comparison to the sims. So things like this. And also noise compatibility, because if you've seen the other workshop, we have to take into account the differences in noise for each of the variables. So if you attach here another set of variables with more or less noise, this will influence your results. So you have to consider this when you're doing that. So just one example, which is not outside of analytical chemistry, but it's not tof-sims. It's to do with something I used to do, which is analyze cultural heritage things or artifacts using ion beams. So we have this external beam that would hit some sample, some artifact that would generate several things, and we could detect like characteristic X-rays or backscattered particles and things like this. And the way this was set up, we could put several detectors around it and get different signals. So from the same spot, if we're doing like a mapping of, for example, from the same spot or each pixel, you can get signal from various detectors. So in this case here, we did it with 3 X-ray detectors optimized for different ranges in energy. So just putting different filters on the window of the X-ray detector. And then we just join everything as a big spectrum. Obviously, if you look at the scale, it won't make sense. This is not the correct energy scale. But we know this, so you only join it for the processing, and then we can go, separate afterwards for the interpretation. But by doing this, we could process everything together in the matrix and get those distribution maps here from the MVA, which will relate to all the peaks or all the signal from all 3 detectors in one single processing step. So that's one of the advantages of doing the column-wise augmentation. You get more information. The other one, which is actually the one I want to talk more about today, is the row-wise augmentation. So here, with the column-wise, we're adding more variables. So you can expect now, in the column-wise, we're adding more samples because we're adding things, adding more rows to your matrix. So we're adding more observations. So notice that the same set of variables is kept, right? The original ones here. We're just adding more stuff. So this could be as simple as adding repeats, things that we typically do, like that we acquire different dates to. You can just add more data to increase the statistics, for example, or you can change the conditions, or you can add standards. So very simple, right? We do this all the time. So, but I want to see how we can apply this to imaging data sets. So if we go again and recap from what we spoke some months ago in the MPA workshop, how we construct a matrix from an imaging data set, right? So when you do an imaging data set, you have all these images, each related to an ion. So essentially what we have is one full spectrum per pixel, right? At each pixel of your image, you can get the information from all the ions, secondary ions. So you have a full spectrum going this direction here. So what we do is we unfold this. So for each of those pixels, we get the spectrum and put it in a row, right? And then we construct exactly the same matrix, right? Each row now is a pixel, and each column is again an ion, a variable. So it's once we do this, we go back to exactly the same situation, but now instead of having samples in the rows, we have pixels of this imaging data set. So, and typically will be very large, right? If you have 256 by 256 pixels, you have 65,000 rows, pixels in total. So if we have 2 imaging data sets and we want to combine them, from different samples that are somehow related, and you want to process them together, we can just do the unfolding for each of those. So we have those matrices. And now, as we saw 2 slides ago, we can just do the row-wise augmentation. So we then join these 2 matrices into one, and we're ready to go to process this as a single matrix. So it's simple. Once you do the unfolding, you can just join it. So, but it can be very powerful, as you show. I will show in the examples. And I think this is a good time to say that years ago, I think the first paper that got me motivated to do this was actually a paper by someone we all know, David. They were doing exactly this. They were just combining different imaging datasets from different spots in this microarray, and then constructing this matrix and processing everything together. Exactly what I described. So this was what inspired me in the first place to do all these things. And I like what they say in the end, is that the study aims to demonstrate a method for automated cross-comparison of individual datasets by analyzing multiple datasets as a single entity. So that's what we're doing, right? We're combining several datasets and analyzing them as a single matrix, single entity. But for imaging, which is much more powerful than just doing individual samples, point spectra. So if you remember, when we do PCA or NMF, we're just factorizing this matrix we just constructed. And when we do this sort of row-wise augmentation, we only have to do this factorization once, and we end up with a consistent set of scores and loadings. Right? So you only have one set of loadings if you do PCA that will be applicable to all the images you join together in this augmentation. And obviously, it's this. This makes more sense if these samples share some similarity. You wouldn't be analyzing a metal sample and a polymer sample in this way, because if you do PCA or things like this, it will just separate all the pixels from one from all the pixels of the other if they don't share anything. So this is useful when you have things that are similar, but you have to do different measurements for each of them, or you have different imaging data sets for them. So this can be very useful. But it can be even more useful, which is what I want to get on. It can be very effective. So to explain this, I wanted to trace this parallel with technical photography. I don't know if you've heard about this before, but when people are taking, again, goes back to when I used to look at cultural heritage things. When you're doing photographs of paintings, for example, we use those things called color checkers. So you include them in the photography so you can have a reference for all the colors, because you want to do systematic assessment of the colors in your photography. So you want to create a database of paintings and things like this. So the idea behind this is it's similar to using a color checker. So here we're combining a color checker with photographs of different paintings. And in SIMS, we will do imaging of pure compounds, homogeneous samples, that we know may be present in a more complex mixture that we also have an imaging data set. So the pure stuff will be acting as your color checker, right? And obviously we cannot, like in the paintings, we cannot photograph things together, right? We have to do separate measurements. Most of the times you won't have the pure stuff next to your complex mixture. So we just analyze them separately and then do the matrix augmentation, which is also sometimes called a stitching. We're just stitching imaging data sets. And then we end up with something like the photograph with the color check in it. So skipping some steps, all you get in the end is, so these are 4 cross sections of complex mixtures. And at the bottom here are the homogeneous reference samples. So without even looking at the peaks of these MVA results, we know where each of these compounds are in our complex ones, because we created a color code for it. So each of the colors are representing a different NMF factor here in this case. or it could be PCA or anything like that, or even some sort of clustering. But the important thing is, if you're not worried about the specificity of what peaks make up each of those things, you just want to see where they are. If you use the standards and combine the matrices, by processing them together, you will see their distributions in this very effective way. It's even effective to present because it's very quick to match the green to green and the pink to pink, or different colors you may choose. So, but I'm showing you obviously the nice thing about NMF is you also get the characteristic signal for each of the factors or n members. But it may not be necessary if you just want to see where each of these individual compounds are in your complex mixture. And some techniques will do this in a sort of what we call supervised ways, where you fix a component to be, or NMF n member to be, a specific spectrum, and then you force everything else to adapt to it. In this case here, we're not doing this, we're just adding homogeneous samples to the data set, and the analysis is still unsupervised. It's still, the method is still figuring out where things are without you telling anything. You're just adding things to help in a way. Obviously, you're driving the solution to have these pure compounds, but you're not forcing the algorithm to do it. But again, yeah, this is acting as your color checker. So now, with the whole picture, this is it's in the paper. It's just showing the whole process, right? So in this case here, each of those cross sections were also made of different smaller mapping data sets. So which is the same as doing some large area imaging. We're just stitching different patches, right? So we stitch everything together, unfold it, find the factors, the loadings and scores and etc., and then fold it back to see the distributions. And because you know where each sample was in the stitching process, you can see where things are distributed. So this is one of the examples that we just showed, I think 3 others, and then try to do a practical demonstration. So here, for example, is we're working with this filament. We're making a filament that's based on 2 different kinds of fibers. It's a composite material. So we have the polymer fibers, the carbon fibers. In green is the carbon, and in blue here is the polymer. Where we made a cross section, embedding everything in a resin, organic resin, and then cutting. So what I want to see is after we process this filament, we're hoping that the polymer will melt and mix well with the carbon fibers. But we don't know whether it will mix as well with the resin. So what we do is we measure the pure resin. We measure it before the processing and measure it after, which is the one in the center here, and process everything as a single matrix using the exact method I just described. So what we end up with is 3 NMF n members, one referring to each of those compounds, so the polymer, the carbon fiber, and the embedding resin. And now we can see exactly what's going on in each of the cases. So we don't have to do 3 different data processing steps. So we just create a single matrix, process everything is consistent, and we can see what's going on. And obviously in this case here, we're also using this to see whether we could identify the same thing using optical images. So we do the Sims analysis once using this very robust, consistent method, and then we just assess the optical images later for several repeats. Another one that can be useful for many of us is how we do like depth profile of 3D data sets. We can then get images of different depth levels. So this is like 50 seconds on the top left here, 50 seconds photo time, and then 100 seconds, 150, 200 seconds. And you can see the things are changing. And we added, so we get those imaging data sets referring to specific depth levels, but we also added to this data set the reference ink data. So we measured those specific inks separately, and to create these homogeneous mapping data sets and add it to the same matrix. So when we process, again, the factors will show these two organic materials, and you can see now how they distribute or how they change as you go in depth or as you increase the sputter time. So, and you can see they're very similar, right? So it's quite useful because sometimes you get results like this purple and green, and you're not sure if it's real or if it's just some noise or some artifact. But this is really reassuring because in the reference inks, it's clearly purple for this one and clearly green for this one. So you can trust that this is a good solution. Again, yeah, these two here acting as the color checker. I was just trying to force this comparison. Finally, this, we're not using the color checker in this one, but what we did was we're stitching different images in that will refer to different periods of time in this kind of corrosion behavior or corrosion protection from this lithium-based inhibitor. So like 15 seconds to 48 hours, how things change. So we just have different samples. Instead of analyzing them individually, we just stitch everything together and process, which makes things very consistent, very easy to present, and it's much more reliable in a way. Yeah, so now I finished with the example, so I want to do some practical demonstration, but before I do that, I just want to check if anyone's got any question.
Got a side okay.
Yeah, your voice is a bit cracking.
Okay, I think this happens a lot, and I might just question instead. You can learn to articulate as well.
So I didn't get that. Is my voice cracking as well?
No, your voice is fine.
Can you type your question, Bill? I will set up the demonstration while you type it. Multiple variables. What do you mean? Like the one with the different detectors in the X-ray? Like the column-wise augmentation? Or not for today? I do have, yeah, like that paper, I'm one of the authors, so I can maybe show another day or show you later. But yeah, I do have examples of multiple variables. And some people like merge positive and negative polarity as well. No, yeah, sims and other techniques. No, I don't think I have any example. Yeah. What I did before was combine X-ray data with like social, because it was looking at teeth from children, and we're using like their age and their weight and stuff like this as variables as well to see if it correlates to the chemistry. So it's not sims. But I can show you this as well another time. But I didn't prepare this for today. Sorry. So I'm just setting up the demonstration. Okay, if there's no more questions, I will start the demonstration. Is that okay? Right, so some of you may be familiar with Sims and VA. Again, if you're not, we had another workshop where I tried to show the main features. So for today, because we don't have much time, we just assume we're all familiar with it. So we create a new imaging tab. So when we go to the load button, we can go like load file, and then it gives you the option of stitching data. So stitch data, then asks you the pixel binning and the number of rows and columns, which are the important bits. So sorry. It depends on how many data sets you want to join together. So for this first one, we'll do three rows and 4 columns. So the way it's done here in Sims VA, it's trying to make it interactive. It creates one button for each of those patches you want to stitch. So, and then you can click on each of those and then load anything you want to load. So in this case, you'll be loading the BIF6 files, or you can be loading the ASCII files, or loading stuff from your MATLAB workspace as well. So let's go to folder. So as I said, this is from the first example. I will be joining different areas of the same big cross section, because this was sort of a manually done large area measurement. So you'll see as I do it. So I'm loading the first one. So before it loads, it asks you if you want to compress the data, if you want to, sometimes it's the 512 by 512 pixels, you want it to be a bit smaller so that the final image is not too large. So you go specify pixels or specify compression factor. For this one, you're not going to do any compression. So just say no compression, and it loads here. And because of the way I'm doing this, we need to rotate. So there's a rotate button here. And I rotate like this. Then I go to the next one, and I will do it for until I complete the 2 cross sections. So obviously you can arrange any way you want. What we're doing is just joining matrices. As long as you know where things are, it's fine. So I created I added the 2 cross sections here, and now in this bottom row here we'll just add all the reference, my color checker. So once you've added everything, you can click the stitch button. So, and then it loads as if you had this as a single matrix. So we spoke about this before, but it's very important in this case to do the normalization, because you don't know if all these things, you may know, but sometimes all these data sets were not acquired for the same amount of time, and they have different in total ion counts. So it's really good to normalize it by total. So Alinson is moving. So because we want to save time, I will also it's treating this as a single imaging data set. So if I say I want to, let's just for some, yeah, if I want to do some binning, it will do it for all pixels. So it will compress it. It was like 500 or so pixels by 350. It will reduce it to 250 by 180. So it makes it smaller. Obviously, because you know, if we bin too much, we lose the spatial information. So let's do some PCA first. So in the pre-process, we will pick Poisson scale and mean centering. And I'll click the PCA button. Let's have a look at the results. So you can see here, like, let's focus on the scores. PC1, it's showing positive contributions for the substrate of only one of the cross sections. And I know these two cross sections have different substrates. One of them was aluminium, the other one was zinc. So it's probably showing the aluminium peaks here. But obviously we are more concerned about the organic part of the non-substrate. Second principal component is showing the zinc in positive and everything else in the negative. So you can see those metal materials, they're so different than the organic that they will come as the highest variance, which is PC1 and PC2. So we can keep going, we can look at PC3. And then now you're starting to see things related to the organic material. So, for example, the negative stuff, remember we're always checking the color checker at the bottom. So the negative stuff is correlating to only these two references. So you can see it's black for this one and this one, meaning that it's not related to PC3 negative or positive for that matter. But it's interesting to see that it relates to the top surface of both samples, and these references are actually my uncured, if I'm not wrong, I forgot which order it is, but I think it's the uncured materials. That shows that on the top surface my material is more uncured. Maybe it was the cured, but you get the idea. And then you can start getting things that are more related to contaminants, and NPC5 you seem to be getting one of the phases in the positive, and so on. What we did in the paper was do NMF to create that nice image with the color code. So let's do this now. But obviously we had to do PCA first to see how many things are there, and whether or not these samples share differences. So we'll go back here, remove the mean centering. Then do the NMF. I don't remember now. I think we had to do 7 factors. So I'm doing 25% subsampling of the pixels to save time. You will only process 25% of the pixels. Right. So now it's now negative. They all look like spectral stuff. But as I said, let's try not to look at the ions. Let's see if we can identify where each of those things are by only looking at the maps, because we're using this color checker. So the first one, really nice. We can see it's only the second of the standard and is one of the phases in the polymer mixture for both samples. Obviously, the phases in one of them is, the size of the phases are different, and it's to do with how things were processed and perhaps the substrate, because we know one of them was zinc, the other one was aluminium. These, yeah, this is interesting. You can see it shines really bright for the fourth reference, but you can see it's not very strong for the others. It may be that because there's not much there, but you can also try to renormalize it so that all the values add up to 100%. So you can here like normalize by total. Yeah, it helps a bit with not much, or you can normalize by the maximum of the full map. Yeah, so basically you have to play around with the contrast in this case, but you can see there's some, like, it's the other phase. Don't know if you can see it. One completes the other, but it's to do now with these other two, the uncued and cued of the other resin. So you're already able to determine the distribution of these two resins. I think because I did seven instead of 6, it somehow separated the stuff in the actual sample from the reference. Anyway, and then we have this sort of subsurface contamination. One of them is the aluminium substrate, the zinc substrate, and I think it's what we spoke about before, mostly the uncued stuff on the top surface. And that view was done using this overlay functionality. So we click overlay, and we can just select which ones we want to see, like number 1, number 2, number 3. Oh yeah, 2 and 3 I think are the ones that we kind of were the same. I don't know. 4. Let's add everything just to see how it looks. We need more maybe. Yeah, this is limited, yes. So I updated this, but right now it's limited but 6, sorry. But you can change the colors of each of them, or you can use like what I call the base color maps. Some of them are good enough. So like this grid 6. Yeah, and you can also do the extra normalization. You may all be familiar with this already. But yeah, if you normalize by total, it kind of flattens the topography, but it helps with the contrast. And I have this fixed contrast, which is combining normalization by total and by maximum, so it kind of maximize the contrast. So yeah, so you start to see the distribution within your complex cross section and also in your reference samples. You can see here it's not as perfect as I showed in the slides, and the reason is we didn't use enough NMF factors basically. So it's a matter of exploring, but it helps a lot having the standards here, because now we know where they are. Okay. Okay, I will show another one, which is the one with the different depths. But before I need to set it up again, so I will just stop sharing the screen and just see if anyone's got any question. Okay, if there's no questions, I will show the other one. And now I'll use this time as well to, let's see, before I say anything. Yes, I will use it to kind of showcase the future version of Sims if you even trying to make it more compact and kind of not only about Sims, to be honest. So obviously I won't be showing what all these buttons do. I just want to show how you can use the stitching, but maybe you already see, what's coming. So I'll find the load 2D. So basically in this version here we can load 1D, 2D, 3D things using the same interface. You don't have to have a specific tab for specific kinds of data. So you just go to the load 2D, and it's the same idea, stitch data. So let's see this one. We're doing 4 rows by 2 columns. So this is the one where we'll load different depth levels in the depth profile and stitch them as a single image. So it's essentially doing 3D analysis, but treating it as a 2D dataset. And now, to show you, I will not say no compression. For each of those, I will say specify pixels, and I will say I want it to be 128 by 128 pixels. Yeah, and then it loads with the size I asked it to. So this is the first one. We'll just do all of them. It's a bit tedious, but once you do it, you can save as a project and then just load the entire project with the data already stitched. You don't have to do it every time if you want to, explore these different days. So I have all the depth levels, and now we add the 2 reference maps for the 2 inks. In terms of the experiments, what I noticed is it's if you want to get the pure homogeneous stuff, it's sometimes good to do it before and after cleaning with the argon, with GCIB. So you end up with 4 references. Here I'm only adding the cleaned version, but sometimes it's worth doing it before and after cleaning because you don't know how surfaces are. Right, so if we go stitch, yeah, it creates this here. So in this kind of future version, the variables are here on the side, and you can see what's going on. I'm sorry, I don't have much time to explain how it works, but there's a button for normalization now. You click that button, and let's do PCA first. And to save time, I'll compress it a little bit. So you have this pre-MVA panel, and there's a button for mean centering. Once you do it, mean centers, a button for custom scaling. And there's also like this layout feature here where you can just remove panels and just keep the panel you're more interested in. So if we do PCA, it's the same icon as we had before. So we will create all the principal components here, but we need to bring up the MVA panel. Yeah. So I can even remove the original data panel, or just, hide it, and then I only have the MVA results. So as you can see, actually PC1 is enough to show us what we want, right? So you want to see where each of those reference materials are distributed in the depth profile. So you have your color checker at the bottom here. Red is one of the materials, blue is the other, and then you can see where they are at each of those images. And obviously you can look at the loadings here on the right, and it shows you the peaks related to each of these colors. And you're very certain that these are the peaks related to each of those inks, because it shows bright red here for the one on the right, and bright blue for the one on the left. And you know that these are pure samples, reference samples we use. So it gives you the confidence to say, okay, yeah, this is actually the distribution of my materials in depth. So you can select different PC, or you can hold Shift and select a few of them. If you select 4 of them, it will show it in a grid like this. So yeah, I'm just showcasing the new software at the same time. So obviously the other principal components are not really important now for this specific data set, because it was very simple. We just had 2 components, 2 compounds, and we had 2 references which are very pure. But you can see here in the factor 3 for PCA, some contamination. So let's only look at number 3. Yeah, it looks like, yes, look at the red stuff, which is the positive. Sodium and potassium. So this specific reference sample was dirty, right? So it was picked up in PC3. Probably because I cleaned with the argon, otherwise it would have been picked up by PC1, because sodium and potassium have very strong peaks, as we all know. So before we finish, I will just now do NMF with this. So I have to remove the mean centering. So you see the mean centering button is on, so we just turn it off. Quick. Yeah, so now it's the original data. We can keep the bottom scale and the normalization. You can see here. I mean, the labels are a bit messed because I'm still developing this, but yeah, this is normalized by total. So NMF, and actually let's do it with only 2, because that's the number of factors we know are there. So again, it creates here the list of factors. So again, I will hide this panel, and then you can just click through to see the first one. You see at the bottom here on the right, it's very strong for one of the references and practically 0 for the other. And the same happens for number 2, it's very strong for the one on the left, and you can see its distribution. If you select both of them, it will show it in a grid. But you can also click this button here, which will do the overlay that we're just doing for the other one. So showing in red one of them and blue the other one. And you can even overlay the spectra. Not very useful for sims, but for stuff like Raman and things like this, it's nice to see these things overlaid. Here it's a bit confusing. But as I say, I want this to be more to have a wider application than just sims. So yeah, you can see it in a grid or overlaid. And let's, so okay, to finish, let's do another thing. Let's do k-means clustering. So what we want to do is find regions of interest that share the same chemistry. So say I think I want to find 2 regions of interest, and I have to specify some things like filtrations. So let's see if it does what we want. Yeah, so number one. So now we don't have intensities, right? It's either one or the other. So you specify regions. So number two is everything around this blob and also the reference on the left. Number one, the blobs plus the reference on the right. If we select both of them, it overlays like this. And what you see here now is just the average spectrum or the total spectrum inside those regions of interest. So these are real spectra. It's not like the NMF results, which will look like spectra, but they're not necessarily spectra. These are real spectra because just adding all the spectra from the regions of interest, so red and blue colors. You can see it in a grid as well, like that. Okay, so yeah, so as I said before, my hope was to inspire you to apply these methodologies to your data sets if you have references or samples which are very complex. So you may consider buying references and measuring maps to help your MVA analysis, or even combining things in your depth profiles to see how things change using the same methodology. Yeah, that's all I had. Thank you.
Thank you very much, Gus. It was really very interesting. I like your new Sims MVA.
Do you? Okay, that's good.
Yeah.
Yeah, I'm hoping to have some functioning version to share, a test version soon, but it's still a bit broken, so I don't want to share it.
Does anyone have a question?
So Steffi, can you see yourself using this? Like, have you done this before, this sort of augmentation?
No, I haven't done it before, but it's really interesting.
Okay, yeah, it's good to know. Yeah, if you can always send me a Teams message, anyone, if you have more questions, you can send me over the papers, and yeah, I'm open to discussion anytime.
So if there are no more questions for Gus, then I think we're ending this session for today. And thank you very much again.
Welcome.
And next week we have Toba for a talk. And hope to see you all next week, and have a nice weekend.
Thanks, Steffi. Bye. Bye, everyone.
Bye.